Hi, this is Chemo 21, Chapter 2, Sections 2.9 and 2.10. In these last two sections, we're going to talk about density and temperature scales. So density is a quantity that actually has two units in it, mass and volume. It's the ratio of the mass of an object to the volume occupied by that object. Common units for density are grams per centimeter cubed for solids or grams per mil for liquids. And here's just a nice little graphic that shows the density of some common liquid substances. So here's a way you can calculate density if you have a mass and a volume. A certain mineral has a mass of 17.8 grams and a volume of 2.35 centimeters cubed. What is the density of this mineral? So you can just plug in the mass and the volume. And notice this is a solid, so its volume is in centimeters cubed. So the density is the mass divided by the volume, 17.8 divided by 2.35. So the density comes out to 7.57 grams per centimeter cubed. Each one of these numbers has three sig figs, so the answer is going to have three sig figs. These are all measured values. So here's a learning check for you. A liquid has a mass of 23.5 grams and occupies a volume of 125 mils. What is the density of this liquid? So pause your recording, calculate this density. We can see that the density is the mass over the volume, 23.5 divided by 125. Both of these numbers have three sig figs, so the answer, the density, is going to have three sig figs, 0.188 grams over mils. So density can also be used as a conversion factor. So we saw in our dimensional analysis section, section 2.8, the conversion factors had two units in them. And in this case, density has two units, grams and mils. So this problem is asking, what is the mass? So right away, we write down mass over here, grams. What is the mass of a 49.6 mil sample of a liquid, which has a density of 0.85 grams per mil? Well, we're going to start with our 49.6 mils, because that's what they're giving us to start with. We're trying to calculate grams. So we're going to write our conversion factor in the middle, write our line here. We're going to put mils on the bottom and grams on the top. So we're trying to get rid of the mils. We're trying to introduce the grams. We have this conversion factor that's been given to us, the 0.85 grams in a mil. So the 0.85 goes with the gram, and the mils just goes on the bottom. So 49.6 times 0.85 gives us a mass of 42 grams. The answer has two sig figs because density, 0.85 grams per mil, is a measured value. And in multiplication and division problems, the answer has the same number of sig figs as the value with the fewest number, which in this case is 2. So here's a problem for you using density as a conversion factor. How many grams are in 35 mils of ethanol if the density of ethanol is 0.789 grams per mil? So you had a minute to pause the recording. We're trying to find grams in this problem, and we've been given 35 mils to start with. We're trying to find grams, and we're starting with 35 mils. So we're going to put grams here, mils here. We're going to put mils on the bottom and grams on the top. We want the mils to cancel, and we want to introduce our grams. Our conversion factor is the density here, 0.789 grams over mils. So the 0.789 goes with the grams, the mils go on the bottom. We multiply 35.0 times 0.789, and then answer comes out 27.6. Both numbers have three sig figs, so the answer has three sig figs. Now, for most problems that we've seen up until this point, we started with a value that only had a single unit in it. But I mentioned that that was 99% of the time, not all the time. What if we only have a single value in our problem and it has two units in it? What about a problem like this? Ethanol has a density of 0.789 grams over mils. What is the density in milligrams per liter? So they're asking us to find a density in milligrams per liter. They're asking us to find an answer that has two units. What is the density? That's what they're asking for. And using our four-step method, what they're asking for, that's our number one. They're asking for density in milligrams per liter. So we write that down in position number one. And they've only given us one other thing in this problem, and that's the 0.789 grams in a mil. So that's our number two. We start with milligrams per liter. We've been given grams per mil. So to do this problem, we start with our grams over mils. And first, let's convert our grams into milligrams because we have grams here and we want milligrams here. So first, we'll convert our grams into milligrams. Then in the second step, we'll convert our milliliters into liters. We'll put the milliliters on the top and the liters on the bottom. We have to put milliliters on the top in this case because we're starting out with milliliters on the bottom. If we want to get rid of them, we have to put them on the top so that they'll cancel top and bottom. So now we've canceled out the grams, we've canceled out the milliliters, and all we have left is milligrams per liter. So in the case where the problem starts out with 2 units, you have to start the problem with 2 units and end up with 2 units. And you can do it all in one-dimensional analysis string. Convert your grams into milligrams in the first step and your milliliters into liters in the second step. So now we have our grams to mils and milligrams per liter. Now let's come in and put our numbers in. Let's do our milligrams to grams. There is 1 milligram in 0.001 grams. 1 milligram, being 1 with the prefix, in 0.001 grams. And there is 1 milliliter, being 1 with the prefix, in 0.001 liters. 1 milliliter in 0.001 liters. Always be 1 with the prefix, putting the number 1 in front of the prefix. Now, how do we do this in our calculator? 0.789 divided by 0.001 equals divided by 0.001 equals. Do your math left to right, not top to bottom. 0.789 divided by 0.001 equals, divided by 0.001 equals 7.89 times 10 to the 5. 3 sig figs, because the only measured value in this problem is the density. Both conversion factors are defined values. Here's some good density theory and practice problems. They're also in the chapter module. And then finally, we're going to talk just about temperature really briefly, mostly for some more sig fig practice, not because you're going to be doing that many temperature conversions in the class. We're going to talk about these 3 temperature systems: Celsius, which is the metric system unit; Kelvin, which is called the absolute temperature scale; and Fahrenheit, which is the familiar temperature scale that we use. You can see the boiling point of water on all 3 scales: 100 for Celsius, 373 for Kelvin, and 212 for Fahrenheit. The freezing point of water, 0 on the Celsius scale, 273 for the Kelvin scale, and 32 for the Fahrenheit scale. Between freezing and boiling on the Celsius scale is 100 degrees. And on the Fahrenheit scale is 180 degrees. 100 here, 180 here. And that explains the conversion factors here. 100 over 180 explains this 5/9. If you punch in 100 over 180, it'll come out to 5/9. That's why when we convert between Celsius and Fahrenheit, we have to change the size of the degree. Celsius degrees are bigger than Fahrenheit degrees. Fahrenheit degrees are smaller. So when we go between Celsius and Fahrenheit, we have to change the size of the degree. When we convert from Fahrenheit to Celsius, we also have to change the 0 point because water freezes at 0 degrees on the Celsius scale and 32 degrees on the Fahrenheit scale. When you convert from Fahrenheit to Celsius, you subtract the 32 degrees and then change the size of the degree. When you're converting from Celsius to Fahrenheit, you change the size of the degree, then add the 32. That order of operation is really important. Subtract, then multiply, multiply, then add. When you do Celsius to Kelvin conversions up here, you're just changing the numbers. So when you go from Celsius to Kelvin, you're just changing the 0 point from 0 to 273 because the size of the degrees is the same. The size of the degrees are exactly the same. The 273 on the Kelvin scale, that's a measured value. So when you do Celsius to Kelvin conversions, pay attention to your sig figs because 273 is a measured value. When you do Celsius to Fahrenheit, your answer should actually have exactly the same precision at the beginning and the end. And we'll do examples of these so you can see what I'm talking about. So your precision can change when you do Celsius to Kelvin because all you're doing is moving from one scale to the next with the same size of degree. But when you do Celsius to Fahrenheit, you have to pay attention to the precision because none of these are measured values. The 32 isn't measured and the size of the degree is not measured. Only the 273 on the Kelvin scale is a measured value. All the rest of these are defined values. The 0, the 100, the 32, the 212. The 273 is the only measured value on any of these scales. So this conversion is the only one where you have to pay attention to your sig figs. On these Celsius to Fahrenheit, the precision has to be the same before and after. So let's look at some of these examples. First of all, just convert 37 degrees C to Kelvin. So 37 degrees C to Kelvin by adding 273. So when we do this, these are both going to be measured values. So when you get the answer 310, you want that answer to still have the same precision in the ones place, right? Because when you add, your answer has to have the same precision as the least precise value. These are both precise in the ones place, so that means this 0 has to be precise as well. So they're both precise in the ones place, so this answer has to have the same precision. So we have to make that 0 a significant 0 by adding the decimal. What about when we convert 102 degrees Fahrenheit to the Kelvin temperature scale? Well, there is no way to go directly from Fahrenheit to Kelvin. We have to go from Fahrenheit to Celsius, then Celsius to Kelvin. So first go Fahrenheit to Celsius, and then Celsius to Kelvin. So this is going to be a two-step problem. So take the Fahrenheit temperature and convert it to Celsius, and then Celsius to Kelvin. And then we'll look at the sig figs. So the Fahrenheit conversion, first we subtract the 32 and multiply by 5/9. So for Fahrenheit and Celsius conversions, we have to have the same precision before and after. So if this is precise to the ones place, our answer has to be precise to the ones place. There's no measured values in a Fahrenheit to Celsius conversion. So just because this has 3 sig figs in it, don't put your answer to 3 sig figs. You have to have the same precision before and after. But then when you add your 39 to 273, pay attention to your sig figs. This one's precise to the ones place. This one's precise to the ones place. So this one has to be precise to the ones place. So now you have the rules of addition and subtraction. So that's everything. That's the end of this section, and it's the end of chapter 2.